For as long as we've looked up at the night sky, we've known that everything, every star, every planet, every galaxy is moving. Our own Milky Way is no exception. It spins, stretches, and slowly drifts through the cosmic void. But for decades, astronomers have believed that our galaxy is on a collision course, a grand, inevitable encounter with our nearest galactic neighbor, Andromeda. This idea wasn't just speculation, it was treated like destiny, a slow, silent ballet written into the fabric of space-time itself. One day, far in the future, our Milky Way would merge with Andromeda, forming a new, enormous elliptical galaxy, one that scientists called Milkomeda. It sounded poetic. Two majestic spiral galaxies, separated by 2.5 million light-years, slowly drawn together by gravity until they unite in a brilliant, chaotic explosion of stars and gas. Computer simulations showed stars being thrown across the sky like sparks, planetary systems torn apart, and black holes spiraling toward each other in a final gravitational dance. It would take billions of years, but it seemed certain. For astronomers, this collision became a kind of cosmic prophecy, a glimpse into the far future of our home textbooks, documentaries. Even NASA's visualizations painted the same picture. In about 5 billion years, the Milky Way and Andromeda would collide, merge, and give birth to the Milkomeda galaxy, a new, more massive, rounder version of what we once called home. But what if this prophecy was wrong? What if Milkomeda was never destined to exist at all? It all began with a strange discovery. Back in 2012, when astronomers first measured Andromeda's motion in unprecedented detail using the Hubble Space Telescope, they noticed something peculiar. Andromeda wasn't moving much across the sky. It showed almost no sideways motion. It was coming almost straight toward us. From Earth's perspective, its light was slightly blue-shifted, meaning its wavelength was being compressed as it moved in our direction. That blue shift was the smoking gun. Andromeda was approaching us at a mind-bending 110 kilometers per second, roughly 250,000 miles per hour. At that speed, given the distance between our galaxies, a head-on collision in about 4 to 5 billion years seemed inevitable. Every model pointed to the same conclusion. It was the universe's version of fate. Simulations at the time, impressive but relatively simple, treated both galaxies as isolated systems drifting through space, each with their own swarm of stars and gas. They didn't account for every small detail, the pull of smaller satellite galaxies, the effects of dark matter halos, or the complex gravitational tides between all of them. And in those simplified universes, the outcome was always the same: collision, chaos, and rebirth. The Milkomeda galaxy became a powerful symbol, a reminder that even the heavens are temporary, that change and destruction are woven into the story of creation itself. It was comforting, in a strange way, to think that our galaxy's end was written in the stars. Predictable, calculable, certain. But the universe, as it often does, had a twist waiting for us. Because new evidence began to challenge everything we thought we knew. When astronomers used more advanced data from the Gaia Space Observatory, they realized that the Milky Way, Andromeda, and their surrounding dwarf galaxies weren't behaving quite as expected. Tiny galaxies, the large and small Magellanic Clouds orbiting the Milky Way, and the Triangulum galaxy near Andromeda, were tugging on their larger companions in subtle but powerful ways. Those little gravitational nudges, when projected over billions of years, could completely change the final outcome. In other words, our cosmic destiny might not be as fixed as we once believed. Could it be that the Milky Way and Andromeda might never collide at all? That the Milkomeda galaxy, the grand merger we've imagined for decades, is nothing more than a beautiful misunderstanding? In the next chapter, we'll dive deeper into how astronomers realized our prediction of the universe's future might have been a massive cosmic miscalculation, and what that means for the fate and freedom of our galaxy. For decades, astronomers believed they had the future of our galaxy perfectly mapped out. The Milky Way and Andromeda, two titans of the local group, were destined to meet, to merge, to become one. It was, for a long time, one of the few certainties we thought we had about the far future of the universe. But certainty, in science, can be deceptive. As our telescopes improved and our measurements became more precise, cracks began to form in the story we told ourselves. The more we looked, the more we realized that the motion of galaxies isn't as simple as two objects being pulled together by gravity. The universe is not a quiet dance. It's a turbulent gravitational web, a system so complex that even the tiniest influences can completely rewrite the ending. When scientists revisited Andromeda's trajectory using data from the Hubble Space Telescope and later from the Gaia mission, they noticed inconsistencies. Yes, Andromeda is indeed moving toward us. That much was clear. But how straight that path really is and how much it might shift over billions of years was suddenly open to question. You see, galaxies aren't isolated travelers floating through empty space. They exist in clusters, surrounded by smaller companions, faint, less massive galaxies that still exert very real gravitational forces. And our local group is crowded. Orbiting the Milky Way are two such companions, the Large Magellanic Cloud and the Small Magellanic Cloud, each a dwarf galaxy filled with stars and dark matter. They're small compared to us, but in gravitational terms, they matter. They tug on our galaxy, warping its outer disk, bending the paths of stars, and even pulling on our dark matter halo, the vast, invisible sphere that holds our galaxy together. And Andromeda isn't alone either. It has its own entourage, dozens of smaller galaxies, including the Triangulum Galaxy, M33, which is large enough to be noticed even by amateur astronomers with a good telescope. These tiny galaxies, invisible to the naked eye, might seem insignificant when compared to giants like the Milky Way or Andromeda. But their proximity gives them leverage. In cosmic dynamics, mass isn't the only thing that matters. Distance does too. A smaller object that orbits close can exert as much pull as a heavier one that's far away. And over billions of years, those subtle pulls add up. That's where the miscalculation began. Earlier models of the Milky Way-Andromeda collision treated the two galaxies as if they were alone, drifting through an empty void, unaffected by anything else. These simulations were elegant but simplified, like trying to predict the movement of ocean waves without accounting for wind or tides. They ignored the swarm of smaller galaxies orbiting nearby, and most importantly, the dark matter halos that envelop both systems. Each galaxy's halo is enormous, a roughly spherical region extending far beyond its visible stars, composed of invisible, unseen mass that we only detect through gravity. When these halos interact, they don't behave like rigid shells. They distort, stretch, and overlap in ways that can subtly alter the galaxy's paths over unimaginable timescales. When researchers included all of these factors, the Magellanic Clouds, the Triangulum Galaxy, the dark matter halos, and the collective gravitational interactions of dozens of smaller systems, the results changed dramatically. The cosmic certainty of collision began to dissolve into probability. For the first time, simulations began to show alternate futures. In some, the Milky Way and Andromeda still collided head-on, merging into a massive elliptical galaxy. In others, they merely brushed past each other, exchanging streams of stars and gas, but continuing on separate paths. And in a surprising number of cases, they never collided at all. The reason was chaos, literal chaos in the mathematical sense. A chaotic system is one where even the smallest change in initial conditions can lead to vastly different outcomes. And in the grand scale of the cosmos, small changes might mean the gravitational pull of a single dwarf galaxy, or a slight shift in dark matter density somewhere in the void between them. This realization shook one of the most widely accepted predictions in modern astronomy. The Milkomeda galaxy, once considered the inevitable child of two colliding spirals, was no longer guaranteed. It was just one possible outcome among countless others. Some researchers even began to argue that our previous confidence in the Milky Way-Andromeda collision was more of a story than a fact, a narrative built on elegant but incomplete data. Because if the local group truly is a chaotic, interconnected web of moving parts, then predicting its future is like trying to forecast the exact shape of a cloud a million years from now. The truth is, we don't actually know what will happen. The universe, it turns out, doesn't like being predictable. The great cosmic miscalculation wasn't an error in math. It was a reminder of humility, a realization that even with all our telescopes, data, and simulations, we still live inside a universe too vast and complex to fully grasp. In the next part, we'll explore the bold new simulations that changed everything, how scientists used 100,000 virtual universes to test our galaxy's future, and what those experiments revealed about the uncertain fate of the Milky Way and Andromeda. For generations, the story of the Milky Way and Andromeda seemed settled, a collision written in the stars. But in science, belief is never enough. Evidence, models, and data must stand the test of reality. When astronomers began to doubt the old prediction, they decided to challenge it using the most powerful tool they had: simulation. In a universe too vast to experiment with directly, computer models are our laboratories. They allow scientists to take everything we know about physics, gravity, motion, dark matter, cosmic expansion, and compress billions of years of evolution into a few hours of computation. And when the question is the future of our own galaxy, the stakes couldn't be higher. The new generation of simulations didn't start from scratch. They built upon decades of work, but added something that earlier models had ignored: complexity. Instead of treating the Milky Way and Andromeda as two lonely galaxies drifting toward each other, they included everything: the large and small Magellanic Clouds, the Triangulum Galaxy, and dozens of dwarf galaxies that populate the local group. Each one was given its own mass, trajectory, and dark matter halo. The models also accounted for 22 key variables that could influence the outcome. Factors like the galaxy's total mass, their spin orientations, the size and shape of their halos, and even the speed and direction of the universe's subtle expansion in our local region. It was, by far, the most detailed attempt ever made to predict the Milky Way's far future. To capture the range of possible outcomes, scientists turned to a technique called Monte Carlo simulation, a method that repeats a model tens of thousands of times, each time slightly altering the starting conditions. In this case, the astronomers ran over 100,000 simulations of the local group's evolution, letting each one unfold for tens of billions of years. Every run of the simulation represented a different possible universe. In some, the Milky Way and Andromeda collided directly after 5 billion years, creating a massive elliptical galaxy, our long-assumed Milkomeda. In others, the galaxies grazed past one another, swapping streams of stars and dark matter before drifting apart again. And in many others, shockingly many, they never collided at all. When the results were tallied, the numbers told a completely new story. Only about 2% of the simulations ended with the classic, catastrophic merger we've all been taught to expect. The remaining 98% produced outcomes that ranged from near misses to stable coexistence, a cosmic stalemate lasting far longer than the age of the current universe. In some simulations, Andromeda passed close enough to distort the Milky Way's spiral arms, pulling long streams of stars into intergalactic space, but then continued on, fading into the distance. In others, the two galaxies orbited one another for tens of billions of years, caught in a slow gravitational dance that never quite ended in collision. And in a rare few, the two galaxies even drifted apart forever, never meeting, never merging, their light slowly dimming as the universe expanded between them. These results were shocking, even to the researchers themselves. For decades, astronomy students were taught that Milkomeda was the inevitable conclusion of our galactic story. Now, the data suggested that inevitability might have been an illusion. The future wasn't fixed. It was uncertain, probabilistic, and exquisitely sensitive to every unseen influence. One of the key insights from these new models came from examining the role of dark matter halos, those invisible, massive structures that surround every galaxy and account for most of its true mass. When two halos overlap, they don't just pull the galaxies together, they can also act like cushions, absorbing energy, altering orbits, and sometimes preventing a full collision altogether. It turns out the dark matter halos of the Milky Way and Andromeda are already overlapping in part, but their interaction is far more complex than a simple gravitational attraction. Over billions of years, these halos can exchange momentum and energy, changing the galaxy's paths in unpredictable ways. If they slow each other down, a merger becomes more likely. If they transfer momentum outward, for instance through the gravitational influence of smaller galaxies, the systems might actually drift apart. Even the faintest satellite galaxies, which orbit like tiny moons around the Milky Way and Andromeda, can tip the balance. They act as gravitational messengers, subtly shifting the mass distribution and redirecting the flow of energy between the two giants. Over timescales of tens of billions of years, these small effects are amplified, creating entirely different fates. The most surprising result of all? In roughly half of the simulations where no collision occurred within the next 5 billion years, both galaxies managed to retain their elegant spiral shapes. Still beautiful, still distinct, still spinning quietly in the cosmic dark. The other half eventually merged, but only after 20 to 30 billion years, long after the sun would have burned out and Earth turned to dust. That finding alone changes the story we tell about our cosmic future. It suggests that the end of the Milky Way might not come in a fiery galactic collision, but in a slow fading, a quiet survival. And perhaps that's the greater revelation. The idea that the universe doesn't obey a predetermined script, that even galaxies, bound by gravity, still move within a web of uncertainty and chance. Science, at its best, doesn't just tell us what to believe. It teaches us how to question belief itself. And as the simulations continue to evolve, we are reminded of something both humbling and extraordinary. Even the fate of entire galaxies can hinge on the smallest invisible forces. In the final part, we'll explore what this uncertainty means, not only for the future of our galaxy, but for the way we understand destiny itself. Because if the Milky Way's end isn't written, maybe nothing in the universe truly is. For most of human history, we've looked at the stars and searched for patterns, for meaning, for destiny. We wanted the universe to have a plan, a beginning, and an inevitable end. The story of the Milky Way and Andromeda seemed to fit that need perfectly. Two galaxies on a cosmic collision course, fated to become one. It was poetic, almost comforting. But as the simulations grew more complex, as the data became sharper, that comfort began to dissolve into something far more humbling. Because the truth that emerged from the numbers was this: there is no destiny written in the stars. When scientists ran thousands of simulations, each slightly different, each accounting for new gravitational nuances, they discovered not a single future, but a spectrum of possibilities. In some, the Milky Way and Andromeda collided violently, their stars scattering like sparks in a cosmic storm. In others, they merely danced past one another, pulled close by gravity but never quite touching. And in a few rare cases, their paths diverged completely, their gravitational bonds breaking apart under the subtle influence of smaller galaxies and the invisible tides of dark matter. The universe, it seemed, was not a clockwork mechanism ticking toward a fixed outcome. It was a vast, chaotic sea, where even the faintest ripple can reshape the horizon. This realization didn't just change how astronomers think about our galactic future. It changed how we think about prediction itself. Because if the fates of galaxies, entire islands of stars spanning hundreds of thousands of light years, can be altered by something as subtle as the gravity of a dwarf galaxy, then what hope do we have of knowing our own distant fate with certainty? Yet there's beauty in that uncertainty. It reminds us that the cosmos is still alive, dynamic, evolving. Not a script to be read, but a mystery to be explored. Every measurement, every telescope image, is not another step toward final answers, but an invitation to keep asking better questions. Some scientists now wonder if even time itself might be more fluid than we imagine. If cosmic evolution isn't a straight line, but a web of branching paths, each leading to a different version of reality. In that light, the idea of a future Milkomeda isn't a prophecy. It's a possibility, one of many that could emerge depending on how the invisible forces of gravity and dark matter weave their quiet influence across the ages. Perhaps that's the deeper message hidden in the great cosmic miscalculation, that the universe doesn't owe us certainty. It offers us complexity, and with it, wonder. Billions of years from now, long after humanity's time has passed, the Milky Way and Andromeda will still be moving, tracing their slow, silent arcs across the darkness. Maybe they'll collide. Maybe they'll drift apart. Maybe something stranger will happen, something no simulation could ever predict. And that's the point. The universe doesn't follow our expectations. It writes its own story, one we're lucky enough to glimpse, for just a moment, from a small blue world orbiting an ordinary star, in a galaxy whose destiny is anything but certain.